Hello class, welcome back. Today I'm going to be going over the test 2 review and test 3 review. And test 3 is going to go over chapters 8 and chapters 9, where chapters 8 were static and current electricity, and chapter 9 was magnetism and electromagnetic induction. All right, so let's get right into it. The review again is posted on Blackboard under, I think it's week 3 or 4, one of those weeks. But you can find it on there, and I'm just gonna go through that review there. All right, so let's get right into it. So the first question is number 1. Number 1 says the nucleus of an atom is charged. So, let's see, nucleus of an atom. So let me draw that out here. So those are our protons, right, of the atom. And then there's also some neutrons in there. And then here's the electrons out here. But we don't even have to worry about those because we're just looking at the nucleus, right? So the nucleus has these protons, which are going to be the red ones. And we know protons are positively charged, right? Protons are positively charged. And these black ones are going to be the neutrons. And we know those are neutral. Boom. So, basically, the nucleus of an atom is going to have a positive charge. So the answer to number 1 is going to be B. Right, because the nucleus just has protons and neutrons with the electrons that are negative, kind of spinning around it here. All right, so number 2 says the vast number of electrons in a coin don't fly off the surface because A, they are strongly bonded to their atoms, B, mutual repulsion is incomplete, C, they're attracted to an equal number of protons, or D, all of the above. Well, for one, if we just have a coin sitting here, let's say this is our coin. Boom, right? This is our coin. If coin's just sitting there, we know basically this coin is a conductor, right? Because it's a piece of metal. But other than that, this coin is electrically neutral, meaning, yeah, we know there's some electrons and protons in here because it has some atoms, but this coin just sitting by itself has no charge. And so what does it mean for something to have no charge? Well, it means the positive, so positives equal the negatives. Right, so when the positives equal the negatives, that basically means the positive and negatives cancel out, making an object neutral. So this coin is basically neutral. And so what keeps the electrons from flying off is going to be C, because they're attracted to an equal number of protons, or positive. So these negatives are attracted to the positives. And that's what's kind of keeping the electrons from flying off of this coin. And then there's an equal number of them, and that basically makes the coin neutral. So for number 2, the answer is going to be C. All right, so now number 3. 2 positively charged plastic straws near each other tend to what? Well, we know opposites attract, and same repels. Boom. So if we have 2 positively charged straws, so they both have the same charge, they're then gonna both repel. So number 3 is gonna be A. Boom. Number 4 says, when you scuff electrons from the carpet onto your shoes, when you scuff electrons from the carpet onto your shoes, you become what? Polarized, ionized, positively charged, neutralized, or negatively charged. Well, this is kind of like the lab with John Travolta. If you kind of scuff your feet on the ground, you're going to pick up some electrons, or you're going to pick up some negative charge, right? And then once you have that negative charge, if you go to touch another person or another conducting object, that charge is going to transfer from you into whatever that other object is. So basically, you picking up some electrons is just going to make you negatively charged. So the answer to number 4 is E. Number 5 says, a negatively charged rod is brought near a metal can that rests on a wooden table. You touch the opposite side of the can momentarily with your finger. The can then becomes what? Okay, let's see. Number 5. So I've got this rod here. It's negatively charged. It's brought near a can. Alright, let's see. It's brought near a can and you touch the opposite side of the can momentarily with your finger. The can then becomes what? So it either becomes uncharged, positively charged, or negatively charged. So if we just bring this negatively charged rod near this can, it's going to polarize it, right? Or in other words, these negatives from the rod are going to build up kind of on this side. Then so some electrons are going to build up on this side. Because the negatives from this rod are going to attract the positives, and then the negatives from this rod are going to push the negatives onto the opposite side over here. So now if you come and you touch this can, so I'll draw a finger. It's supposed to be a finger. Whatever. So now if you go and touch this can here, basically the negative charges on this can are going to transfer to your finger. So these charges are going to transfer to your finger. Boom. Basically leaving this can to be just positively charged. So the answer to number 5 is going to be B. All right, so now number 6 says, a main difference between gravitational and electric forces is that electric forces attract and repel. Attract are weaker, obey the inverse square law, act over short distances. Well, first of all, we know gravity. Well, let me just write the equations for both. You know, both of these equations look very similar. So gravity would be m d squared. And then we also have the force of electricity, which is going to be K, Q1, Q2 over d squared. Boom. So obviously, we know they both follow the inverse square law. They both act over short distances, meaning the closer two objects get together, the stronger either one of these forces are going to be. So the main difference between gravity and electricity is that the electric force can attract and repel, right? Because charges can be plus or minus. or gravity can only attract, because masses can only be positive. So the answer to number 6 then, number 6 is going to be A, attract or repel. Alright, so number 7 says the electric force between charges is strongest when, so the electric force between charges, write this out again, is strongest when they're close together. Well, that sounds about right, because the smaller the distance is, the stronger the force is, or the closer these two objects are, the more they're going to be attracted to each other. So A sounds like a good answer. B is strongest when they're far apart. Well, we know that's not true. As these two objects get further apart, the force between them gets weaker. And C, either of them. Well, so for number 7, the answer is going to be A. Number 8 says 2 charged particles 1 meter apart exert 1 Newton of force onto each other. If the magnitude is doubled, the force on each particle will be, okay, so basically we're going to be using this equation because we have 2 charged particles and they're 1 meter apart, so D is going to be 1, the force is going to be 1, so this is going to be equal to 1 Newton. This distance D also becomes 1. Alright, so now they say if the magnitude of each one of these charges are doubled, then what happens to the force? So if I double each of those charges, so now I got 2q1 and 2q2, right? Distance is still the same, so I'll put a 1 there. K is still there. So this is my new force now, after doubling these charges. Well, now it's basically 2 times 2, right? That becomes 4. So let me just write a 4 here. Boom, right? So now notice, basically, this whole part of the equation is the same as all this, right? But the only difference here now is just this 4. So this new force, after we double the charges, is going to be 4 times as big. And so I think number 8 has a typo. I think A is supposed to be 4. So the new force is 4 newtons. So number 8 has a typo. Let me write that here, a typo. The answer is A, but it's 4 newtons, not 14. Because if you double both the charges, we'll just have 2 times 2, then you get a 4, making the new force 4 times as big. Alright, so number 9 says, you say an object is electrically polarized. To say that an object is electrically polarized is to say it is electrically charged, it is to some degree magnetic, it is only partially conducting, its charges have been rearranged, its internal electric field is 0. Well, when I tried to describe polarization to you, I gave you some solid object, right? Conducting object, and it has negative and positive charges in it. But it's neutral. Overall, it's neutral because it has positives and negative charges. So this is electrically neutral by itself. So to polarize it really just means when I bring another object, let's say I bring a rod, a charged rod, And this rod has positively charged, positively charged. So when I bring this rod here next to this object, the negatives in this object are going to be attracted to the rod. So the negatives are going to build up over here. It's going to push the positives to the other side. Boom. So now we would say this object here is polarized. So when I say something is polarized, it just means the charges inside that object have been rearranged. So the answer to number 9 is going to be D. All right. Number 10 says the electric field lines about a point charge extend. So we got some point charge here. A, it extends in circles, outwards when it's positive, outwards when it's negative. Well, if we have a positive charge, again, we know it's electric field, points outwards in all directions. And this is how we draw our electric field lines. And for positives, they always point away. Boom. So for number 10, the answer is going to be B. Right? And if we have a negative charge, the arrows are going to point towards it if it were a negative charge. All right, so now number 11 says the electric field between oppositely charged parallel plates is. Okay, so if you have two parallel plates, boom, top plate. It's the bottom plate. Make the bottom plate positively charged. Top plate negatively charged. So we know there's going to be an electric field in between these plates here. And the electric field always points from high to low, or from the positive to the negative. Because again, the electric field always points away from the positive, right? And it always points towards the negative. So the electric field is going to look something like this. Boom. So now the electric field between these two parallel plates that are oppositely charged, this being the electric field in black, this electric field is constant. Constant, or in other words, you could say it's uniform, basically inside this electric field. So basically, like the electric field here is the same as it is here. It's the same as it is here, 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 here. The electric field is the same in all these points inside of it. So for 11, the answer is going to be C. All right, so number 12. Number 12 says food cooked in a microwave oven depends on electrical, a charge polarization, field strength, conduction, resistance changes, or all of the above. All right, so if we draw a microwave here, and I don't know. So this is our microwave. So food cooked in a microwave depends on, well, I don't think I talked about this in any of the slides, but I'll just say it basically depends on A, electrical polarization, charge polarization. Well, So for a microwave, it depends on charge polarization, because a microwave is going to radiate some waves inside of the box here. And then those waves are going to hit whatever it is that you're trying to warm up. And then those waves basically polarize the atoms inside of this food that you're trying to warm up. And it basically heats it up as it's polarizing it, because the waves kind of hit it over and over. So long story short, the answer is going to be A for 12. Number 13 says electric potential. Number 13. Electric potential is the ratio of electric energy to the amount of electric what? Well, electric energy, let's see, how am I going to write this? Well, V is for the electric potential, right? Q charge. So this is the electric potential. This is the charge. And so the electric potential times the charge gives you this is the electric potential energy. Boom. So the voltage, or the electric potential, which is, this is voltage, times the charge gives you the electric potential energy. So it says the electric potential is the ratio of the electric energy to its amount of electric what. So you can rewrite this equation this way. So this says electric potential equals the electric potential energy divided by the charge. And so the answer here to 13 is going to be A, the charge. All right, so 14 says when a battery does 24 joules of work on 10 coulombs of charge, the voltage it supplies is, well, actually, we're going to use this equation for that. So number 14, so a battery does 24 joules of work or energy. And so potential energy is basically a form of energy, right? And so we have basically the voltage is going to be equal to 24 joules, because that's the energy, divided by 10 coulombs, because that's the charge. So we can just divide these two to give us the voltage. And the voltage is going to be 2.4 volts. So 14 is going to be D. All right, 15. Says a sustained electric current can be achieved with a battery, a generator, or both. Well, we know a battery basically can supply energy through a current, while a generator, we know, also generates electrical currents. So the answer for 15 is going to be C. No trick there. Batteries supply energy, and generators obviously supply energy. Number 16. Says the amount of energy given to each coulomb of charge flowing through a 12-volt battery. So this goes back to the potential energy voltage times charge equation. So we're trying to find the amount of electrical energy given to each charge flowing through 12 volts. So it's basically 12 times 1 time for each charge. And it's just going to be 12 joules. And it's in joules, right? Because we're trying to find the amount of energy. So the answer to 16 is going to be C. 17 says electrons flow in a wire when there's a potential difference across the ends, an imbalance of charges in the wire, a difference in potential energy across its ends. Okay, so if we have, draw it like this. It's our battery, it's our wire. So we know basically a current is going to go through this wire. And a current is going to flow through this wire because there is this power supply or this battery, which gives it a voltage. And we know voltage is basically potential difference, right? So the only thing that's causing a current to flow in this wire here is basically this potential difference caused by this battery. So this is basically a voltage. It's also a potential difference. Yeah, so basically these two words are interchangeable. So when I say voltage, I also mean potential difference. When I say potential difference, I also mean voltage. You know, again, let's say it's something like 5 volts. 5 volts, that would be the potential difference. And then if we want to also find the current, we would use V equals IR, where this R is going to be the resistance, and that'd be the resistance of this wire, because this wire probably has some amount of resistance to it. And then I would be the current flowing through the wire. So the answer to 17 is going to be A. It's the potential difference right here across the ends of the wire. So like this is the front, this is the end. There's a potential difference between them. Number 18 says the flow of electrons in a circuit moved by A, colliding with molecules, B, interacting with an established electric field, or C, bumping other electrons. So the answer here is 18. So for one, it's not A. It's not going to be A because the electrons are not necessarily colliding with other molecules, because it's only the, well, I guess other molecules would be like something else is inside of the material. So it's not colliding with other molecules. Interacting with an established electric field. That one sounds a bit more correct, because whenever there's a potential difference, there's also an electric field. So for example, if I go back to this parallel plate scenario, where the electric field points this way, well, this is the electric field between these two plates. Well, there's also a potential difference. Between those plates. So whenever there's a potential difference, there's also an electric field. And then basically inside of this electric field, electrons can move, right? So like if I were to put an electron down here, it would want to move upwards. And that's basically what happens inside of a wire. There's some potential difference here. And it's causing the electrons to go around because it's an electric field inside of this wire caused by this potential difference. So all that to say, the answer to 18 is going to be B. All right, number 19. Number 19 says the electric current in a copper wire is normally composed of ions, electrons, or protons, right? Number 19. Oops, yeah. So I might have mentioned this like a few times before, but whenever there is a current inside of a wire, whenever there's a current, it's really just the electrons that are flowing. The protons are part of the nucleus, right, of the atom. So it's not like the nucleus of the atom is moving. It's just the electrons on the outer ring of the atom are moving. So if this is our atom over here, these protons that are in the nucleus are not moving, but the electrons out here are being shared. Those can move around. So imagine we have a whole bunch of these atoms inside of this wire. And then once we put a potential difference or connect a battery to it, then the electrons are free to move. Basically, the electrons are going to be pushed away from the bottom end, right? And then kind of go around. And so it's the electrons that are basically causing the current, or is what the current is composed of. So the answer to number 19 is going to be B. But also note that even though we know the electrons are going in this direction, we always say the current is in the direction opposite to the electrons, because electrons have a negative charge, right? So this would be like a negative current. So instead of saying negative current, we just say the positive current is going in the opposite direction. So we always use basically the current coming from the positive end going to the negative end, but we know physically it's actually just the electrons going the opposite way. But just to make it easier, we say the current's going in from the high to the low, or in its positive direction. So let's see, that was 19. Number 20 says, to say a current is DC is to say the current. So number 19, or what am I on, 20? Number 20, basically it says, talks about a DC current. DC equals direct current. And that just means it flows in one direction. So number 20 is going to be, C. So DC means direct current, which means current flows in one direction, while AC equals alternating. It's an alternating current, which means the current flips back and forth. It just doesn't go one way. The first is this way, then it's that way, then it's this way, then it's that way. Current goes back and forth for AC, or alternating current. 21 says a direct current is normally produced by a direct current is produced by usually a battery, right? Because whenever we have like some circuit, if we put a battery in it, we know that's going to produce some current going in one direction. This is the battery here. So the answer to 21 is going to be B. Okay, so next 22 says, let me see here. 22. When we say an appliance uses up electricity, we are actually saying that electrons are taken out of the circuit and put somewhere else. Not necessarily. B, the main power supply voltage is lower. No, definitely not. Electrical charges are dissipated. Definitely not. Electrical charge changes to thermal energy and current disappears. So let me just tell you why the ones that are wrong and why which one is right. So let me start at the bottom. E is not right because current never disappears. Even though a current can stop, it doesn't necessarily disappear. And that's definitely not what they mean by when an appliance uses up electricity. Electric charges are dissipated. Again, that's kind of like the last one. Electric charges cannot be dissipated. Of course, that kind of goes back to the law of energy. Energy can't be created nor destroyed. So charges, which is a form of energy, just cannot dissipate, but they can change form. Electrons are taken out of the circuit and put somewhere else. No, electrons are not being taken out of the circuit. Electrons basically just supply the current. They're not actually being taken out of the wire itself, right? So like we don't have to replace wires because the wire has all of the current taken out of it. So basically I'm just going to tell you then the answer is going to be D for 22. Electrical energy changes to thermal energy. So we know that fits the law of conservation of energy, because energy cannot be created nor destroyed, but it can change forms. So when electricity is used up, it's used up in the form of heat or temperature. So that's why the answer is D. 22, 23 says, which of these, all of the same length, has a greater electrical resistance? So it's like we have iron, an iron ball, B, rubber, C, copper, and D, all of the above. Well, we know iron and copper are both conductors, right? So this is a conductor. That's right, conduct. This is a conductor. Conduct. Rubber is, we know, an insulator. Insulator. It basically means you can't put a charge through anything made of rubber, but you can put a charge through iron or copper, because both of those are conductors. So the answer here, which one has the greatest resistance? Well, it must be rubber, right? Because the more resistance something has, basically means the harder it is to push a current through it. And so rubber must have a really, really high resistance because it's an insulator. So the answer is going to be B for 23. let's see, 24 says a length of wire has a resistance R. Same kind of wire. Okay. "24 says a length of wire has a resistance R. So the same kind of wire has twice the length. So here's some wire. Let's say it's the wire with twice the length. Boom. All right, so we see this second wire is made out of the same material, but it's twice as long. So how does that affect the resistance? Well, there's two things that affect the resistance of an object, right? It is temperature. So the hotter something is, so temperature, I'm going to write it this way. Temperature, the hotter the wire is, the higher the resistance. Then also the longer that wire is, the higher the resistance. Then also the thinner it is. So I'm right, thinner, the higher the resistance. So if you raise the temperature, that raises the resistance. If you make it longer, that raises the resistance. If you make it thinner, then that also raises the resistance. Excuse me. So here, if we double the length, basically that also doubles the resistance. And if you like to, I don't know, if you like equations, the equation that would prove that is this equation. Resistance equals this little p that we call a rho, which is resistivity, L divided by A. Where this L is basically the length of the wire, and this A is the area of the wire. Not how long it is, but like the area. So if this were a circle, it would be that area there. That area. That's what that A would be. So see, we have the length up here. So if it gets longer, if the length is longer, that increases the resistance. We see the area is on the bottom. So if the area gets bigger, then the resistance gets lower because it's on the bottom. So the answer here is going to be A, which is 2R. Let's see, 25 says more current will occur in a lamp when its filament is, when it's hot or cold. So if we have some lamp, this is our lamp. If we want this lamp to shine brighter, we can either, add more voltage to the power supply, right? So like add more batteries, that would make it shine brighter, right? But let's say we just have this one battery and we want this to shine brighter. Well, we know if the resistance is lower, so basically if you lower the resistance, that would increase the current. Again, it's kind of think of these things in terms of like water flowing through a river. So if there's less resistance in a river, then the river can flow a lot better. So if the resistance is less, we'll shine brighter. So if resistance is less, is lowered, I said lowered, it will shine brighter. So how can we lower this resistance in terms of temperature? Well, I said a moment ago, right? If you increase the temperature, that increases the resistance. But we want to lower the resistance, so we want this to be colder. Because if we lower the temperature, then the resistance gets lower. If the resistance is lower, more current can flow through. And if more current can flow through, then it can shine brighter. So the answer to 25 is going to be A. All right, 26 says the current in a conductor can be increased by so here's our conductor, and we're trying to increase this current, right? Yeah, trying to increase the current. So if we reduce the resistance, which is A, if we reduce the resistance, that would increase the current, right? No, basically kind of what I said a moment ago. Or B, we can increase the voltage or add more batteries. Well, that would also increase the current. And so actually 26 is going to be C. It's going to be both of those. Either lower the resistance, you can either lower this, or you can add more voltage to increase the current. All right, 27 says the current through two identical light bulbs is the same, and they're in series. So we've got a light bulb here, a light bulb here. Boom. So both of these light bulbs have a current of 0.25. Write that over here. Current equals 0.25. And the voltage across the bulb, the voltage is equal to 110. This is volts, amps. The resistance of a single light bulb is what? So we want to find the resistance, let's say, of this single light bulb. Well, we know that let's see. We know they both have the same current, right? So let's do it like this. If we know both of these have the same current, we kind of have to do this question backwards, because they both have the same current. So if they both have the same current, they must both have the same resistance. Because if this one had a higher resistance, then it would have a lower current, or vice versa. So the fact that they have the same current means that they have the same resistance. So let me call this resistance R, and I'll call this resistance R. So now if I use my Ohm's law, it's going to be V with the total voltage equals the current times R, the total R. Where the total R is basically these two added up. So R total equals 2R. All right, and we're trying to solve for what? We're trying to solve for this resistance for one of them. So I can divide the current over. So we have the resistance total equals total voltage here divided by the current I. So that's basically 110 divided by 0.25. And that is, let's check the calculator. 110 divided by 0.25 is 440. And so now that gives us the total resistance, or our total. And so that's the resistance for both of those. So now we have, if I rewrite this equation, we have 440 equals R total. And we know R total is 2R because there's 2 resistors. So now just to solve for one of the R's, we just divide 2 over. And so dividing 2 over, that gives us 220. Boom. So the answer here for 27 is going to be A. All right. So this question here, a little bit more tricky, a little bit more math involved. If you didn't get anything, we just watch this part again, take it slow. I'll try to re-emphasize what I did here. So first, it says the current through both of these is the same. And since the current through both of those were the same, I knew they both must have the same resistance. And so then using our Ohm's law, where we have to use Ohm's law for the whole thing. So we have the total voltage, or this total voltage here, is equal to the total current, well, we know the current for both of them is 0.25 times the total resistance, which is the resistance for both of these light bulbs put together, which is just 2R. So then dividing the total voltage by the current, was able to find the total resistance. And then from the total resistance, we knew it was equal to 2 resistors. So then we could divide that and solve for just one of the resistors. All right, so now 28 then. 28 says a bird can sit harmlessly on a high voltage wire because A, no potential difference is across the bird's feet, the wire is insulated, the net charge on the current carrying wire is 0, current is inside, not outside the wire. So the answer to 28 is going to be A, pretty sure. Because basically a potential difference is what causes some type of charge transfer. And if there's no potential difference, there'll be no charge transfer. So no potential difference equals no charge transfer. So the answer, I think, is going to be A. Number 29 says the current through a 10 ohm resistor connected to a power supply of 120 is, well, we know V equals IR, where this is Ohm's law. And we're trying to solve for the current. So current equals voltage divided by resistance. The voltage is 120, the resistance is 10. So the current is going to be 12 amps, which is C. Number 30 says, compared to the amount of current that flows from a battery into a circuit, the amount of current that returns to the battery is, well, so if we have this battery here connected to the wire, we know some current comes out of it over here. And so that same amount of current always goes back to the battery. So basically for number 30 here, the answer is going to be B, the same. So the same amount of flow that comes out, or the same amount of current that flows out, is the same amount of current that flows in. Number 31 says 2 lamps, a thick filament and a thin one, are connected in parallel to a battery. Okay. Say this is the thin one. Say this is the thick one. Right. Boom. So this is our circuit. We got these 2 light bulbs. They're connected in parallel. And this is our thin filament. This is our thick filament. And it says here the lamp, the current is greater in which of these lamps? Well, we know that if the wire is thinner, the resistance increases. So let me write this. So if it's a thin wire, we have a high resistance. If it's a thick wire, then we have a low resistance. Boom. So just from kind of knowing this part here, we know this thicker filament light bulb is going to have more of a current flowing through it. So the answer here for 31 is going to be A. All right. Let's see. 30. Well, that was 32. 32 is A. Now 33. Number 33 says a pair of 1 ohm resistors are connected in series. So here's our resistors. They're connected in series. The resistance of both of those is 1. So now it's asking us what is the combined resistance. Well, this is kind of similar to that light bulb problem I did. So our total here, our total is basically 2 times 1, or 1 plus 1. Basically add them up. So you could do 1 plus 1, or you could do 2 times 1, because they're both the same. Either way, it's going to give you 2. But basically, we just add them up. So let's see, the resistance then is going to be B. A total resistance. It's going to be 2. You can just add these up. So now number 34 says, the headlights, radio, defroster fan, and an automobile are connected in what? Well, if we have an object, let's connect it in series. Let me just say this first. So let's say we have like these light bulbs connected in series here. If this light bulb here breaks, if that light bulb breaks, and put another one here, and another one here. If this light bulb here breaks, then all of these other light bulbs are gonna go out because they're all connected in series. So basically, you have to have all the lights working for if you just want one of them working. But we know an automobile is different because you can have the radio on with the AC off, or you can have the AC on with the radio off, or, you know, different combination of things. You got the headlights on, but the radio off, you know? So in order for them to run kind of independently, they must be in parallel. Because we have things in parallel, then let's say this one breaks, then the other two appliances can still run because a current can still flow through them, even though this object here is either broken or off. So the answer to number 34 is they are in parallel. All right, number 35 says we have a 4 ohm and a 6 ohm. Number 35. We have these two resistors in parallel. This is R, this is R. Let's say this one's 4, this one's 6. And we're trying to find the equivalent resistance. Well, we know when we have resistors in series, that increases the resistance. So if we have a resistor in parallel, that decreases the resistance. And the way we add that up is, so for parallel, the total resistance, I'm gonna use RT, is 1 over R1 plus 1 over R2, dot, dot, dot. So if there were more, then it would just kind of keep adding up this way. So 1 over the total resistance is going to be 1 over 4 plus 1 over 6, right? Now, you probably just use your calculator to add that up to give you, let me see, I'm going to use my calculator, 1 over 4 plus 1 over 6. Looks like that's about 0.417. And so now we're trying to solve for RT, right? So kind of have to like flip it. So basically RT is going to be equal to 1 over that there, 0.417. So now we do 1 divided by 0.417, and we get the total resistance is 2.4. So notice that the total resistance is less than both of those because they're in parallel. And so that's going to be B. All right, 36 now. 36 says, what is the power rating of a device that draws? So we're talking about power here. We're going to power equals voltage times current. And we're trying to find what this power is when it draws 0.8 amps of current and it's connected to 120 volts. So here we just multiply the voltage and the current, and let's see, we get 120 times 0.8, 96. 96 watts. And that's going to be D. Okay, so now 37, now moving on to magnetism. So 37 says, like kinds of magnetic poles repel, while unlike kinds of magnetic poles, well, they attract. That's pretty straightforward. That's going to be B for 37. 38 says magnet A has twice the magnetic field of B and pulls on B with the force of 100 newtons. So let me try to draw that out this way. So we got this big magnet and we got this small magnet. Boom. So big magnet, small magnet. And just to give you like a similar scenario, let's say we have the Earth really, really big, Moon little over here. We know that the Earth is attracting the Moon because they're two masses, right? They're attracted through gravity. So the Earth is attracting the Moon, and the Moon is also attracting the Earth. Well, same thing here. We got this big magnet. It's attracting this smaller magnet, and the smaller magnet is attracting the bigger magnet. So I'm giving you these two parallels because basically kind of the same thing is happening here. We have these two objects interacting through one force. Here they're interacting through the magnetic force. Here they're interacting through the gravitational force. So even though the Earth is bigger or the Moon is smaller, they attract each other with the same force in different directions. So they attract with the same force. They attract with the same force. This is basically Newton's third law, right? Every action has an equal opposite reaction. So these two attract with the same force. They're just in opposite directions. Same thing goes for these magnets. Even though this one's bigger, this one's pulling on the bigger one too in that direction with the same amount of force. So these two magnets are attracting each other with the same amount of force, just in opposite directions. So the answer here for 38 is going to be B. Because they're going to attract each other with the same force, just how the Earth and the Moon attract each other with the same force, just in opposite directions. 39 says every spinning electron is, so if you have a tiny electron here and it's spinning, well, we know an electron for one is electrically charged, so A would be true. And because it's electrically charged and it's moving, it also has, a magnetic field. So it kind of has like a North Pole and a South Pole. So this little spinning electron can also be thought of as a tiny magnet. Remember, basically it's electrons and objects that cause them to be magnetic. So this is electrically charged and it's kind of a tiny magnet. So 39 is C. 40 says a magnet will become weaker if dropped on a hard surface or held in a hot flame. Well, neither one of those are true. Neither one of those affect how the strength of a magnet. Um, 41 says several paper clips dangle from the North Pole of a magnet. So we got our magnet here. This is the North Pole. And we have a bunch of paper clips hanging from it. Boom, here's one, here's one, here's one. And it says the induced pole on the bottom of the lowermost magnet. So here, the bottom of the lowermost magnet is what? Well, in order for this clip to be attracted to that North Pole, it must be a South Pole on this side. And if it's a South Pole on that side, it must make this bottom side a North Pole. Then I must make this a South Pole. Then I makes this a North Pole. Then I makes this a South Pole. And so at the very bottom then we have a North Pole. So 41, the answer is going to be A. 42 says the magnetic field lines about a straight wire. 42, magnetic field lines of a straight current carrying wire. So we know since magnetic fields are caused by moving charges, this wire here has a current, so it has some moving charge, so it must have some magnetic field. And the way we know that it's going around is, it's kind of like a right-hand rule, but for straight wires. Use my thumb, remember? So my thumb points in the direction of the current, and then my fingers kind of curl around like this as I close them. So my fingers here are going to represent the magnetic field. So the magnetic field goes around in the direction that my fingers were curling. So the magnetic field circles around this wire here. So the answer to 42 is going to be A. All right. 43 says the number of loops in a current carrying coil is increased, the magnetic field becomes, okay. So we have some wire that's going around like this. So the way the magnetic field looks here is, let's see. Basically, so for this kind of setup, the magnetic field points along the inside of the wire, kind of like that, and then it kind of wraps around out here, and then it kind of goes out, goes out, goes out, goes out. But inside of the coil, the electric field, or the magnetic field, is going straight in one direction. So if I were to increase the loops of this wire, so if I were to increase the loops, that basically is going to increase the magnetic field inside of this solenoid. We basically call this a solenoid when the wire is wrapped up a lot of times. So more loops equal a stronger magnetic field. And so the answer to 43 is, 43 is going to be C, stronger, if you add more loops. Number 44 says the magnetic field inside a current carrying coil increases when the number of loops of the coil increases. Well, we know that's true. The current is increased. Well, if you increase the current, you also increase the magnetic field, so that's also true. You insert an iron core. So if I have these loops here, they basically say if I put in an iron core, something like that. Well, we know iron can be magnetized. Basically, you can turn iron into a magnet if iron becomes in contact with the magnet, it will become a magnet. Kind of like the whole paperclip thing. The paperclip by itself is not a magnet, but once the paperclip touches another magnet, then that paperclip becomes magnetic. So it's also true then if you insert an iron core, that it increases the magnetic field. So the answer to 44 is going to be D. 45 says the magnetic force acts more strongly on a current carrying wire when it is perpendicular to a magnetic field, carries a very large current, either either or both of these. Okay. So 45 says we have some current carrying wire here, and they're asking us about the magnetic force. Well, we know if this wire is inside of some magnetic field, say the magnetic field is going, actually let's do it. I'm gonna do the magnetic field this way. Boom. So the magnetic field is going into the board, right? And the current's going to the right. The magnetic force here then is going to be using the right-hand rule. My thumb is going to be in the direction of the current. My fingers are in the direction of the magnetic field. So my fingers are going to be pointing downwards. Kind of hard to do, but my fingers are going to be down. My thumb to the right. Then my palm points upwards. So the magnetic force here is going to be upwards. That's going to be the force. And then that force is basically given by the charge times the velocity times the magnetic field. So if you increase the magnetic field, that increases the force. If you increase the velocity or increase the current, then that increases the force. So basically the answer here is going to be C. So when the current is very, very big, that increases the force. And when the magnetic field is perpendicular, we're here meaning perpendicular meaning at a right angle. And here the magnetic field is at a right angle with the current. So now 46 says the intensity of cosmic rays bombarding the Earth is greatest at the equators, the mid-latitudes, no particular location, or at the poles. Well, we know the Earth has some North Pole, some South Pole. So kind of think of the Earth kind of like a magnet, because it has some North Pole and some South Pole. Earth also has some magnetic field, right? Going like this. So cosmic rays are charged particles. So cosmic rays are charged particles. I spelled that wrong. Try that again. There we go. Cosmic rays are charged particles. So that means if they're charged, they're going to be attracted to either the north or the south pole, depending on whatever their charges are, right? So positive charges are going to be attracted toward the north. Negative charges are going to be attracted towards the south. And basically that is what causes the, the northern lights at the North Pole, the aurora borealis, where it's all those pretty little colors in the sky. Those are basically caused by charged particles coming in through the North Pole. So the answer to number 46 is going to be D, the poles. All right. 47 says since magnetic force on a moving charge is always perpendicular to its direction of motion, magnetic force is unable to change an electron's, well, it's basically unable to change the electron's speed. Let me see if I can explain why here. So if we have some, this is our proton, right? This proton is gonna come in with some velocity into this magnetic field. And it's gonna experience a magnetic force in the upwards direction. Again, using my thumb, the right-hand rule, thumb in the direction of the velocity, fingers are gonna be downwards. So my palm points upwards. So the force is going to be upwards here. So basically, once that charged particle gets inside, it's going to circle around and come back out over here with that same velocity. So let me do the right-hand rule again for these other points. So at this point up here, now the velocity is upwards, and my fingers are going to point downwards. And so the force is going to be pointing inwards. Boom. So basically this force causes it to kind of curve around this way. Then once it gets here, the force is pointing inwards some more. It's causing it to come around this way. And then it flies straight out. So notice the velocity is different because it's pointing in different directions. Remember, velocity is speed and direction, but the speed is the same. So it has the same, let's say 30 miles per hour here, same 30 miles per hour here, same 30 miles per hour here. The velocity is different because this is 30 miles per hour towards the east. This is 30 miles per hour towards the north. And this is 30 miles per hour towards the west or the left. So the magnetic field only changes the direction. It cannot change the speed. So the magnetic force can't change speed. So the answer to what number was this? Number 47 is going to be B. All right, almost done here. So 48 says electromagnetic induction occurs in a coil whenever there is a charge. Oh, a change, excuse me, whenever there's a change in, well, electromagnetic induction, again, remember, was discovered by Faraday because we knew that moving charges made magnetic fields. So then after we discovered that, we also discovered we can go the other way around. We can say changing or moving, say moving / changing mag fields produce basically currents. So a moving charge makes a magnetic field. A moving magnetic field, sorry about my handwriting, it says moving / changing. So a moving or changing magnetic field produces a current. So 48 says electromagnetic induction in a coil occurs when there is a change in the magnetic field. So if you change the magnetic field, that's going to produce a current. So the answer for 48 is going to be, D. Where are we at? 49 says voltage can be induced in a wire by so we're trying to induce a current in a wire by moving a magnet near the wire, moving the wire near a magnet, changing the current in a nearby wire. Well, we know A is right because A is moving a magnet towards the wire, and that just goes into electromagnetic induction. So moving or changing the magnetic field induces a current, or vice versa, moving the wire near a magnet, that will also induce a current. And C is also true. If you change the current in a nearby wire, So just explain that real quick. Let's say we have some wire here and we increase the current. So this wire here, it's not just a steady current, we're increasing the current. And so if we increase in the current, we're increasing the magnetic field that goes around it, right? So here we have a changing magnetic field because this magnetic field is getting bigger near this other wire. That change in magnetic field from this wire induces a current in this wire in some direction. So basically the answer to 49 is going to be D, all of the above. So whenever basically something is changing or moving, that's when things are being induced. So number 50 says when a bar magnet is thrust at the same speed into a coil having twice the number of loops, the induced voltage is what? Well, we know if we increase the number of loops, if we increase the loops, that basically increases what? The magnetic field. But then that also increases the current. So if it's twice as many loops, then it's going to be twice as much the current. So the answer to 50 then is going to be D, twice as much. All right, 51. 51 says voltage produced by a generator alternates because effectively it is an AC motor in reverse. It produces pulses of current. The current it produces alternates. Or the magnetic field produces alternates. Let's see. So basically, the answer to number 51 is going to be E. The way an alternator or a generator works is we have some magnet, right? This is the north, this is the south pole. So the magnet here is magnet here. And then we have some type of wire, kind of like this. And, it's connected to a battery or actually a light bulb or something. So basically this magnetic field is inducing a current inside of this basically loop here, and that loop is spinning around. And so since that loop is spinning around, the magnetic field produced by that loop basically alternates, causing the current to alternate in this wire. All right, so 52 says, which of these statements is true? A battery and a generator produce AC or alternating current. 52, well, A, we know that's false. B, a battery produces direct current, a generator produces alternating current. That's true. C, a battery and a generator produce direct current. That's false. D, a battery produces AC. Well, that's false. So 52 is going to be B because batteries produce direct currents, generators produce alternating currents. All right, 53 says the rate of which a transformer transfers energy. So basically the rate is 53 says the rate of which a transformer transfers energy is called, basically that's the definition of power. And power is given by voltage times current. So power is basically the rate of which energy is transferred. All right, 54 says transformers use AC, so there will be the required transfer energy from coil to coil, magnetic field intensities, change in input current, change in magnetic field operation. Well, here number 54 is going to be, it's going to be C, a change in the input current. Oops, excuse me, change D, change in the magnetic fields, because the change in the magnetic fields are what produces the alternating current, right? So in order for a transformer to work, the magnetic field must be alternating, and that's going to give you an alternating current. All right, number 55 says the voltage across the input terminals of a transformer is 100 volts. And the primary coil has 50 loops. The secondary coil has 100 loops. The output voltage is what? Well, basically the primary voltage divided by the number of loops. I'm using N for number of loops, equals the secondary voltage for the number of loops for the secondary. So I'm using V for voltage and N for number of loops. So the primary has a voltage of 110. So this is 110, and it has 50 loops. And this has 100 loops. So to solve for this secondary voltage, we would just multiply 10 over and then divide by 50. So we have 110 times 100 divided by 50. So the secondary voltage is going to be 220. That's going to be C. All right, two more. For 56, says a current of 4 amps exists in a primary coil of a transformer powered with 110 volts. What is the power output of the secondary coil? Well, so we're going over transformers right now. Number 56. So for transformers, the power in always equals the power out. So the amount of power you put into the system always equals the amount of power put out. And we know power is given by voltage times current. And the voltage and the current are 110 times 4. So that gives us 110 times 4. That's going to give us 440 watts. So this same amount of power that we put in is going to be the same amount of power that we get out. So 56 is going to be C. Now, lastly, 57. 57 says an electronic game requires 6 volts of operation. With the transformer, it can be powered with 120 volt outlets. Okay. So this is the voltage primary divided by the number of loops primary, voltage secondary, number of loops secondary. The primary voltage is 120. And number of turns are 500. The secondary voltage is 6. And we're trying to find the secondary number of loops. All right, so now basically I have to multiply this over to that side. So rewriting this, we get basically the number of secondary loops. Well, actually, just flip the whole thing, right? Boom, like that. Then I'll just multiply the 6 over. So we have 500 times 6. 500 times 6 divided by 120 equals 25. So the number of secondary loops has to be 25. And that's going to be A. All right, so that's it for the review. Apologize for the video being so long, but there's a lot of questions, a few more than usual, but I hope this helps out. I hope you're able to understand some of these questions a little bit better, and good luck for your test this week.